Okay. Yes. All right, well, go ahead. I realize removing my glasses makes it so I can be seen easier. What's going on? All right, pouring into class. Awesome. Well, go ahead and get started. This is for HVR110, week 4, lesson 2. We're going to start tonight. We're going over chapter 12, is what we'll be discussing. Okay, there we go. Wrong button. So, chapter 12, what we're talking about is electronic control devices. So, what we're going to cover tonight is more or less components of control boards. So we'll talk about what makes a control board, what parts and components are made up of it, and then a little bit of how to troubleshoot them, what you're going to look for when you're dealing with a control board, what to, what you should expect, what's unexpected, and then basically the purpose of them, different styles of them, all sorts of stuff we're going to get into. After this, we'll go into chapter 13 tonight, and that's going to be it for our lecture for this evening. So we should be able to finish this up by 9:40 really easily. So I'll go ahead and get started. So again, electronic control devices, starting off, the main thing we're going to be talking about, like I said, is the fact that electronic control circuits are going to be used in pretty much everything we have for heating and air conditioning. The main reason why we have to have control circuits and control wiring is because when it comes to heating and air conditioning, we're trying to protect the investment of the equipment, so the last thing we want to have is a compressor that's just hooked up straight to power. It's got one switch, and that's it. That's the only thing that determines whether or not that compressor is on or off is a single switch. Instead, we're going to use more controls. We're going to use safety devices. We're going to use temperature sensors and things like that. Stuff we talked about previously in chapter 10 is some of the control devices we talked about for motor controls and motor safety. We're also going to talk about for overall safety of our unit. We can make it so that it's not just the safety of it, but also the efficiency. We can make something run more efficiently by giving it more information. One of the things we'll talk about is thermistors tonight, and they basically upgrade a thermostat from being able to read the temperature just in the room where the thermostat is to now it reads the temperature in all the rooms, and it can adjust the temperature in all the rooms. So again, more information we give a system, the more opportunity we're going to give it to be able to adjust itself and make itself be running basically at an optimal level at all times. So basically, imagine if you had it where every day you control the gas mileage on a car you drive to be the peak gas mileage. It doesn't matter if you're city, it doesn't matter if you're highway, you're getting that highway high mileage the whole time. That's what we're trying to do with these systems. That's why we introduce more and more controls to them, to make it so that they get that peak performance and that peak energy efficiency more regularly, and it's more controlled, it's more consistent, and there's a lot of things we're going to look into. There's solid state devices, there's electronic controls and all this kind of stuff we're going to be seeing. Again, don't forget that all these slides are up on Canvas, so if you miss anything, you can always go back and download those offline. We'll get right into it. We'll start with semiconductors. Now, semiconductors, they are the first part of the whole modern control system. Used to be, if it was a control device, it was very simple. It just meant that it was a smaller electronic component, something that instead of running off of 120 volts, only ran off of 24. So the coil on the bottom of a contactor, the coil inside of a relay, the voltage out of the thermostat, that was all running off of low voltage. And it worked just off of literally electricity passing through with, you know, basic switches turning on and off. With a semiconductor, you can kind of control that flow of electricity more, and you can make it do more things while it's flowing, basically. This allows us to have it where it's no longer simply an on-off situation. We can start to fluctuate, and we can slow and quicken the speed and the flow of the electricity within that semiconductor. So if we use a control board, we can actually wire in different things into that semiconductor control board to make it so that it creates these paths with various levels of resistance that take different amounts of time. So what it leads to is you've got it where the devices are able to be time controlled and time delayed without having to have, you know, a literal timer on them or anything like that. It can just have instead of having to have a timer set on it or something like that, it just has a semiconductor that knows, okay, this is the amount of time that the electricity should take to pass through here, and it'll automatically be delayed through that. So semiconductors, very much the basic of the electric devices that come about with electronic controls. The main thing to understand with this is if you ever see anything that says semiconductor or solid state in your books, or when you're reading, or when you're looking online or researching, it's just talking about control boards. That's what that's referring to. Especially if you see solid state, that is a big indicator that you're dealing with control boards. So don't be intimidated by it. Now, the thing that is more common nowadays is we're going beyond just including a semiconductor as our means of control for this electrical flow. Now we use things like diodes and rectifiers. They're both very similar to each other. Basically, a diode is going to make it so that the current flows in one direction. Now, when we're dealing with current for, or electricity for, a HVAC system, remember, we're dealing with our, let's see if I can get this to work today. We're dealing with that sine wave, that big up, down, up again. All right, so that's our AC current. Oh my gosh, this looks like a third grader did this, but it's okay. That's AC current. Now DC current, at the top here, you've got positive, you got negative, you got neutral, neutral, positive, negative. DC current looks more or less like little hills. It just goes up to positive and then back down to neutral. It's going to go in a single direction. Now, how this can help out is with modern systems, they use AC electricity and they bring it up to the control board. They get it all the way to there, all right, as AC electricity. And the reason why we take it where we're traveling long distances, we take AC electricity, is because it travels better over long distances. DC electricity going long distances will drop voltage very rapidly unless the wires are extremely large. I mean, to a point where when at the dawn of the century, at 1900s kind of thing, late 1800s, when they were first trying to put electricity into cities, they didn't know how to put in AC electricity. DC was the first kind. Well, they had so many power lines, and the power lines were so large that you had a power plant every mile. Every mile you had a power plant, not a substation, a power plant producing power. It was every mile you had to have one. And the wires were so thick on the cables going above people's heads and everything like that. There were areas in New York City where you could look up in midday and not see the sun because it just needs that huge wiring, that massive voltage, and it just can't carry electricity a long distance. But a short distance, like a foot or 3 feet or 5 feet, it can do very easily without having to make massive wiring adjustments or anything like that. So for modern systems, what they use, They use diodes and rectifiers to change AC current and electricity. They change it from AC to DC when it gets to the system, when it gets to the compressor, when it gets to the outdoor fan motor or the blower motor. Now, the reason why they've switched and they've started doing this is because DC electricity can very slowly ramp up its speed. And this is what allows for modern systems to do that modulating control. So we have it where motors and systems can either have one of three options. Nowadays, they're either going to be single speed, multi-speed, or modulating. Now, single speed means it's on or it's off. It's either 0% or 100%. That's it. Multi-speed obviously means that it's going to have more than one speed. Usually 2 is what most of them started out as. They had 2 speeds, whether that was a 2-speed gas furnace, a 2-speed air conditioner or compressor. That was really common. But nowadays, for the past about, let's say, 10 years or so, especially residentially, it's becoming much more common to see this modulating control where everything's coming in as AC electricity, getting changed to DC electricity, and then we've got it where now instead of being 0 or 100 for the single speed, or 50% and 100% for the 2-speed, now we got it with a modulating. It can go from 0 to 100 at 1% at a time, basically. That's the whole thing. It's just very incremental amounts. So as it needs to produce more cooling or more of a refrigeration effect, or as it needs to produce more heat for heating, it can actually react to that based on, hey, what's the temperature outside and what's the temperature inside? How much is the difference? And it learns all of these different things. So that has to do with that DC control. That's why a lot of stuff is now including diodes and rectifiers. And just to show you guys, diode is typically going to look something like this. All right, that's typically what your electric signal for a diode is going to look like. Y'all have it. If you look on your meters, there is a symbol that looks like this because you have it where you can test for a diode. You can make sure that it's working. You want to make sure that it's only allowing electricity to flow. When it comes out this other side, it's only flowing in one direction. On this side, it's still that AC wavy stuff kind of thing. And then this side, you've got it where it's only going in one direction. So that's kind of how that's going to be working for you. Okay. Trying out that drawing thing now, just because I learned how to do that today. So I might be showing it off a little bit. Transistors, if you've ever heard of a transistor, you may have heard it in a song or something like that about a transistor radio. It was a groundbreaking technology in the 1960s. It was what allowed a radio to go from being something that took up, the size of a dresser to now it takes out, oh, well, it's, in your hand, it's a pocket, kind of thing. So this was the start of, electronics getting smaller and smaller and smaller, and now to the point where everyone's got a computer in their pocket. So it's just where things are going. But for heating and air conditioning, the transistor is a component of the control board. It's going to be a part that allows for our control board to actually, send voltage in different directions and to allow it to transfer that electricity how it needs to. It can go through different resistances, but that transistor really, it's going to be pretty basic. You're not going to have to test transistors. You're not going to be a transistor replacement technician or anything like that. The main thing to understand as far as for your quizzes and tests and all that kind of stuff is right here in the middle where it's talking about the types of material. So for a transistor, it's only going to have 2 types of material it's made of, either N-type material or P-type material. And it's really simple as far as how the transistor is constructed. You can tell just by what type of transistor it is. So PNP means that it's P-type material, N-type material, P-type material, one right after the other. NPN would be N-type material, P-type material, N-type material. So it's going to be just those 1, 2, 3 right in a row with each other. Again, your book talks a little bit more about transistors, but you can see they're a very, very small part it's not worth it for our time and effort to try and replace a transistor on a control board. It's much cheaper just to buy a new control board and to install that. It's what it's getting down to nowadays most of the time. But transistors, yeah, they're going to be one of the big components, one of the biggest components that you'll see all in pretty much every single control board. You're going to see these little silver cylinders all over them. That's going to be very, very common. Now, triacs, they're a similar thing to a diode. Your book also has symbols and information on that as well. But basically, two diodes, all right, in a single part is a triac. And what it's going to do is current can pass in both directions once a certain amperage or current is reached. Typically, it's about 1 amp for most of them, but again, depends on the board and the manufacturer and all that kind of stuff. But you basically have a alternating current sitting there facing each other at the edges of the triac, and then once the amperage builds up enough, it'll actually, instead of making it go in one direction after it goes through the diode, it'll allow it to go in both directions through it. Basically, that amperage is going to overload it and override what the diode would normally do. Again, these systems, you're not going to be troubleshooting triacs, so you don't have to worry about, oh my gosh, am I going to have to, get a soldering gun and have to learn how to work on and put together electronic control boards. No, we're not getting to that point really. I've never seen anyone get to that point just because it's not worth the time. It's much, much cheaper to buy a control board. They're not that much. They cost, the most I've seen some, they do cost a lot. The new ones like $1,500, but old school back in the day control boards like $150, maybe $250. So it's not a crazy amount. But the main thing to understand with the control board is to make sure that you don't misdiagnose it. That's one of the biggest mistakes guys will have, is people will rush to the conclusion, well, I've checked my contactor, I've checked my transformer, I've checked this, I've checked that, and they all seem to be working, but I'm just going to say it's the control board because, that's an easy solution. I don't have to check any more components. I'm just going to call that, swap out the control board, and see if it runs. I know guys that have done that for their troubleshooting. They literally just, I'm just going to swap out this control board and see if it works. If it doesn't, then it's something else. And they might have a multi-purpose or a universal control board on their truck that they can keep using again and again and again, or for a couple of different units. But typically, it's going to be, it's just best to understand what that control board's doing and how to troubleshoot it. Is more or less what we'll talk about towards the end of this slideshow is what we call black box method. That's basically just checking voltage in, voltage out. But we'll talk about that more as we keep going through. So LEDs, this is one of the things that, unlike triacs and diodes and everything like that, you're going to see this on a very, very regular basis, and this is going to help you out a lot. All right, so you've probably heard about LEDs. You probably bought a TV or a phone or a screen of some sort that's got LED lighting or as an LED screen. And it stands for what it says right there on the first bullet, light emitting diodes. That's what LED stands for. What it is a diode, which again makes electricity flow in one direction, goes to alternating current to basically DC. And when we control that flow of electricity, it can actually, we can make it emit light. So the nice thing about the light emitting diodes is that for a control board, they can actually wire it in and used as a diagnostic tool for you. So depending on the manufacturer, the typical setup is that at the indoor unit, and for modern systems nowadays, also at the outdoor condensing unit outside, you'll have two sets of control boards. On each control board will be a light emitting diode that will blink and will give you a code. Now, most of the time, if the system's working, it will still be blinking. But what that blinking is usually meaning, it'll blink like 3 times, and that just means either standby or it's operating or it's in normal, mode kind of thing. The easy ones are the ones where it just, instead of when it's operating, it just goes to a standing light as opposed to any sort of blinking. But it's going to use blinking to communicate to you as a technician what's going on with the system. So typically for indoor units, for the gas furnaces especially, a gas furnace is going to have a safety on it. When you take off the panel to get access to the control board, all right, you're going to be entering an area that's got high voltage and low voltage. To protect Joe Schmo, who thinks I watched a YouTube video and I know how to fix my furnace, from hurting himself, all furnaces are equipped with a switch. As soon as you take that panel off, the switch opens and disconnects power to everything inside of there. That includes that LED light. And the LED is going to have an error code. Now, on the panel, before you take it off, before that switch activates and everything like that, there should usually be, it's like a plastic sight glass is what it'll look like, and it lines up pretty much right over the LED on the furnace. And that way, if there's an error, you can actually just see and watch it, and you can sit there, watch for that sight glass and see, okay, how many blinks do I have? It's going to be 2 sets typically, 1 set of slow blinks and 1 set of fast blinks. Depending on the manufacturer, the first set, usually it's the slow LEDs are your first number, and your second number are the fast blinks. So if it does, 3 slow blinks, 1, 2, 3, and then 3 fast blinks, 1, 2, 3, that means your error code is 33. So you look on the control board panel, you look on that cover of that you pull off, and on the inside or the outside of it, it'll have a list of error codes. For these modern systems, it's really common to, it'll happen where, oh, what if the error codes are destroyed, or I can't read them, or I can't get to them, or whatever's happening with it. All you got to do is go online, look at the model number, look at the manufacturer, find that information, and that'll actually give you those error codes as well. You can usually find them in the install guide, so that you don't have to worry about, wondering, oh, what does 33 mean? It could be that it's normal, could mean that everything's broken. So with these, again, it's not going to be the fact that it's going to tell you, hey, replace this part with the error code. It's going to tell you this is what failed recently. So that's all it's really going to be going over. Now, thermistors, this is our next component that we're going to be seeing a lot of use. Thermistors are going to be resistors that change with resistance in temperature. All right, so basically it's a temperature sensor. That's what a thermistor is used as. We can see them used in a lot of different locations, both for safety applications and for controls. For safety, a thermistor is typically going to be seen on most furnaces and electric heaters. Anything that's going to be producing heat, it will have a thermistor typically on it to make sure that it's not producing too much heat or overheating. They can be used on compressor casings, on the housing for a fan motor. You can use it on the exterior of a heat exchanger for a gas furnace. Again, lots of different styles of them where they can be used. For controls, I said about it, I talked about it, I hinted at it basically at the beginning, that with the modern control systems, you have it where zone controlling is very, very common. Now, the thing with zone controlling is you have it where basically, imagine a house, all the rooms are each their own individual zone and their own, temperature and everything like that. You go in a house, every room's got its own temperature. You're going to have your hot room, going to have your cold room. It's just what occurs. But the thermistors can actually be used to even the temperature out. So you still have just one thermostat, and that would control whether or not the system's in heat mode or cool mode or what temperature it's set to. So let's say we have the main thermostat sitting in the downstairs hallway on the first floor of a 2-story house. All right, on that first floor, it's reading 73. We're doing fine, nice and toasty, no problems here. But upstairs, we have it now where we can put thermistors in each of the room, and they can feed back information to the main thermostat telling it yes or no if it's gotten to that temperature. And as it gets to that temperature that the thermostat's set at, it will open and close dampers inside of the ductwork to either allow airflow to go to those rooms or to stop airflow. Oh, it's gotten to temperature, stop the airflow. We don't need to go in it. It doesn't need to get any cooler, doesn't need to get any hotter. This cuts down on the runtime of a system for heating a house, because it'll heat up basically, it'll start by heating the whole place, and then as each room reaches temperature, it'll shut off each damper, and then finally, it slows down and it's heated up that last room. Everyone's nice and toasty, and no one's overheating. So you're not wasting energy by that. That's the big thing, is when you do that overheating, you're just wasting energy. About every degree you increase temperature on a thermostat, you're adding about 3% to an energy bill of a household. So it's really, really expensive to operate a system that way. So instead, having it where it's got these thermistor controls is pretty much what's allowing modern systems to be really, really, really energy efficient and make sure that they send temperature only where it needs to go. This is used a lot of times in commercial applications, but I've seen it in a lot of homes as well. Residences are getting more and more zone controls and dampers and thermistors in them. Now, at the bottom of this, it talks about two different types of thermistors as far as the coefficient, temperature, blah, blah. Okay, so the main thing to understand with this is saying positive temperature coefficient increases as the temperature increases, and the negative temperature coefficient increases as the temperature decreases. What it's talking about is the amount of resistance in that thermistor is going to change for a positive temperature one as the temperature increases, because positive, that's when we're going to have an increase in resistance. For the negative, as the temperature decreases, we'll have an increase in resistance. And that's how the system can actually, by that electrical resistance, is able to know, okay, yes, we are at the correct temperature or not. So thermistors are used in a lot of different applications. The basic controls and electronic circuits, again, like I said, generally it's going to be DC. That's what you're going to see most of the time. They use a diode rectifier. Depending on the style of it, I know there was a style that used to look this weird, crazy symbol. But you've got it where it looks like 4 diodes kind of set up in a triangle. Oh, good Lord. Oh my God. I'm so bad at this. And not a triangle, a diamond. I'm drawing triangles. But you got like 4 diodes is what it's kind of looking like. That's what it's supposed to be, at least. And this is what a rectifier is kind of going to look like, depending on, or at least one of the styles of them. And this is what's going to change AC into DC. And when we change that AC to DC, this is what allows for us to have it where, if we look down here at the bottom, we've got all these little tiny components and parts and small wiring connections and everything like that. Because we've got DC electricity, because we're traveling short distances, we can use very, very small wiring and very, very small resistors and controls compared to if we had to make this all out of AC components or anything like that. This can handle, this is going to be just operating on that DC electricity to send signals, to send information, and to turn systems on and off. This right here, honestly, this control board in the bottom right is, good Lord, like the most basic control board I've ever seen. It's more often than not, they're going to be much larger than that with a lot more components going on. So do not be surprised if you come across them and they're 3, 4, 10 times that size. It's just what happens. But you can look on this thing and you can see a couple of different things that we talked about already. These little cylinders right here, that's going to be your capacitors. You've got these this big black box right here is going to be a relay. These little cylinders with the stripes on them, those are resistors. You can see right here, this little tiny black cylinder right there, that is a transistor. And so we've got all these different parts that we've already talked about, but they're going to be all put together on this control board to allow it to operate properly. So a simple temperature control, the most common one you're going to see is a thermostat. It's the most common one you're going to run into. It's the most common one you're going to operate. Whether you're working with refrigeration, whether you're working with ice making or with residential heating and air conditioning or commercial air conditioning. Thermostats are used on all of our components to set the temperature, all right? They're not going to control the temperature. They're what's going to set the temperature. They're the main thing that says, yes, this is the temperature I need to be set at, and we need to maintain this set temperature. So you've got it where for most systems, all right, for a switch, or again, try and see how I do. All right. So a switch, this is a normally open, closing on a rise switch, and then, oh, crap. Okay. So this is a normally open, closing on a rise switch. This is the second one is normally open, closing on a fall. All right, this symbol I'm adding underneath here, this is for temperature, is what that symbol means. This is going to be what you would see as your, oh Lord, can I write? Cool and heat. All right, so for cooling and for heating, the temperature switch, as far as its basic controls, are going to be this. Cooling thermostat, or the cooling switch, as the temperature rises, it gets closer and closer to that set temperature. Let's say we're set at 74 right here, all right? Down here, the switch is down at 72, and then as it gets closer and closer to 74, it's gonna close, it's gonna complete that path, and then 24 volts of electricity that's sitting on this side is gonna be sent out to our different control components, whether that's our control circuit board, whether that's our thermistors, our contactors, our relays, and that's what's going to turn on our different components. For heating, it works a little bit different. It's going to be the opposite. So as the temperature falls, so this is open on a rise, and then as the temperature falls, as it gets cooler and cooler, that will close and make contact and complete a path across for that heating to take place. It's, again, same thing. 24-volt signal is going to be sent out, and it's going to go out to our different controls, our relays, our contactors, to turn on those different devices and everything like that. So as far as the very, very basics of it, that's what you're going to see a lot of times, just at least cooling and heating. And you've got it where, you know, depending on how complicated you want it to get, you can add more and more switches, more and more cooling and heating controls to make it so that you've got more control over a space. That's the whole idea with it. Okay, lost my mouse for a second. So, like I said before, at the beginning, solid state controls. That's a key word. Solid state means that you're going to be dealing with control boards. So you've got it where this one where it's talking about specifically the controls of one function electronic controls. These are like we saw in that first image of a control board, that very, very small, tiny board. That's these one function devices. These are going to be turn the fan on, make sure that the fan's got multiple speeds, or make sure that the motor isn't going to hurt itself because it's, you know, not cooled down enough or hasn't been given enough time. Things like that. That's what we're going to look at. So the first one we're going to see is an electronic timer. Now, these are very, very common. They're usually nowadays, they're going to be integrated and built into the board. And you'll still see these switches used as far as these actual manual time delay switches, pretty common as well. And you can see it goes from 0.03 minutes, which is, I did the math earlier today, was like 1.8 seconds. So basically no time delay at all, to 10 minutes of time delay. And what this is basically you've got it where power comes in, all right, one leg, and then power is going to go out the other leg to our load, to our compressor, to our condenser fan motor, whatever. But inside of here, this is going to have it where it's got a timer. And that timer, if it's, now this is a delay on make timer. We'll talk about the difference between that and a delay on break in a minute. At least next slide, or yeah, should be the next slide before we I should be able to get to that before we close up this time slot. The time delay, the whole idea behind it and the benefit of it is the fact that it's going to stop us from turning on a unit over and over and over and over again. It's going to give the unit a break. It's going to force the system to wait a certain amount of time. Typically, most are set between 3 and 5 minutes. Typically. I don't say always, I say typically. You're going to see it where one of the biggest things I would say as far as a technician for you to learn is to not trust yourself with how long you think 5 minutes is. You don't know how long 5 minutes is until you've waited 5 minutes. And trust me, even then, you don't know how long 5 minutes is. It's a weird amount of time to keep in your head. The trick to it is have a watch, start a stopwatch when you reset a system. Because if I turn the power off, turn the power on, that resets that 5-minute timer. Every time I do that, every time that I have to take power out of the system and put power back into it, which is going to happen anytime that I need to take out a part, put in a new part, take out a part just to examine it and test it maybe on resistance or something like that, anytime I need to take out wiring. So that's when this kind of adds up, because if I do that 3, 4, 5 times, well, that's 25 minutes of me just waiting, not working on the system, waiting to work on the system. So making sure when you disconnect power, make sure it's time to disconnect it and everything like that, that you can't do anything else. But also with this delay system, make sure you start a stopwatch, wait the 5 minutes. Don't, because the worst thing you can do is go to 4 minutes and 59 seconds and say, oh man, I think it's been 5 minutes. Let me turn the power off again, and I'll get it back on in a minute. And then you go back and you get to, you turn it, you get the system back on, and okay, now it ran this time because you actually waited the full 5 minutes instead of 4 minutes 59 seconds, which has happened to me. I've been there. So stopwatch on your watch or stopwatch on your phone, just some way make it manually count those 5 minutes. Plus, also if you're just waiting for those 5 minutes, if a customer comes down and you're in the basement sitting on your butt just looking at the furnace, you can at least let them know, oh, it's on a delay. I'm just waiting for. I've only got 2 minutes left. As opposed to, oh, it's on a 5-minute delay. I don't know when it's going to start again. That it's just more information. Plus, makes your job just way easier and gives you less of a headache at the end of the day. These can be installed aftermarket as well. They don't have to be installed by the manufacturer. You can put a time delay relay like these ones here on just about any compressor motor or any system that you see out there nowadays, just because it's a good safety to have. It's going to prevent that short cycling from occurring. And when short cycling occurs, it's going to really burn out a motor and hurt most of our components. All right, so the last thing about these electronic timers as far as for this session right now, you've got 2 different styles, the delay on make and the delay on break. So delay on make delays, on delays closing of the device for a predetermined time period. So this is what I was talking about before with those compressors. This is what's going to make it where, hey, give it 5. It's part of the union. We've got discussions. It gets a 5-minute break between each cycle at minimum. If you think it's not going to get that much, you're wrong. That's basically what the timer does. It acts as the union boss for that compressor to make sure it gets its full 5-minute break. And that allows for the compressor to cool off. It allows for the residual electricity and magnetism to leave the wiring and everything like that, so we don't have to deal with all that. And that just makes life a lot easier. Delay on break timers, these are a little bit different. Basically, they're going to keep a component on after something else turns off. So really common for a delay on break timer is for blower motors. So you've got gas furnaces heating up a heat exchanger, or you've got oil furnace heating up a heat exchanger, or a electronic heat strip where it's just a coil of electricity that heats up. Well, that gets really high temperature. All of these different heating components we've got to make sure they cool off enough. Delay on brake timers are used a lot of times to keep that blower fan, the fan that moves the air inside of the building, to keep that fan on long enough to cool off that heat exchanger or to cool off those coils, so we don't end up with an overheated device or component. So that's when they're used a lot of times. They're very, very common for that. But you know, it makes a lot of sense. It's going to make sure, okay, yes, we've cooled it off enough. We're good. We're not going to have to worry about overheating or anything like that. All right, we're going to start again at 7, not 7, sorry. We just finished the 7 o'clock one. We're going to start again at 8 o'clock, and we'll go for another 40 minutes. I will see you guys then.
Hey, Mr. Williams.
Yes, sir.
Are you gonna give us like a study guide for the final exam?
Yeah,